Hello students, in previous class we discussed about Pauli exclusive principle, above principle. Today in this class we are discussing about Hund's rule. Okay, so what is that Hund's rule? Now we will discuss. According to this rule, electron pairing in orbital starts only when all available empty orbitals of the same energy are singly occupied. Okay, so according to this rule, electron pairing in orbital starts when all the available empty orbitals of the same energy are singly occupied. Okay, for example, the configuration of carbon. Okay, configuration of carbon atom is 1s2 2s2 2p2. What is the atomic number of carbon? Atomic number of carbon is 6 and its electronic configuration is 1s2 2s2 2p2. So here the first 4 electrons entering into the 1s and 2s orbitals, and the next 2 electrons go into separate 2p orbitals with both electrons having the same spin. So note that the unpaired electron in the 2p orbitals are shown with parallel spins. Okay, so this Hund's rule is explaining electron pairing in orbital starts only when all available empty orbitals of the same energy are singly occupied. For example, take p orbital. In that p orbitals, px, py, pz suborbitals, there are not there. Okay, so in this, how the electrons will be filled? First electron entering into px orbital, next second electron entering into py orbital, and third electron entering into pz orbitals. Okay, so here all the orbitals, these all empty orbitals are occupied with single electron. Okay, in that p orbital, px, py, pz, there no, this px, py, pz, these all 3 orbitals are occupied with a single electron. So after that pairing will be start, means in each orbital we can fill 2 electrons, no. So here first px, py, pz, that are occupied with a single electron, then after pairing will be start. Okay, px 1 electron is there, py 1 electron will be filled, pz 1 electron will be filled. If again some more electrons are there, no, then fourth electron is entering into px orbital with opposite spin. Fifth electron entering into py orbital with opposite spin. Sixth electron entering into pz orbital with opposite spin. Okay, so Hund's rule is explaining electron pairing in orbital starts only when all the available empty orbitals of the same energy are singly occupied. Okay, so empty orbitals of the same energy are first singly occupied. After that electron pairing will be start. About this Hund's rule will explain. Okay, so now we will understood about this Hund's rule with one example. Okay, so carbon, it is one of the elements, its atomic number 6. So what is its electronic configuration? Its electronic configuration 1s2 2s2 2p2. Okay, so in this first electron entering into 1s orbital and second electron pairing with the first electron in the 1s orbital. Okay, so next 2s2, in that one electron entering into 2s orbital and one more second electron pairing with the first electron in the 2s orbital. Okay, na? Next means in this first 4 electrons, carbon atomic number 6, no, its electronic configuration 1s2 2s2 2p2, no, in that first 4 electrons are entering into 1s2 and 2s2. Okay, so here the configuration of carbon atom Z, electronic atom, carbon atomic number 6, its electronic configuration 1s2 2s2 2p2. In that first 4 electrons are entering into 1s orbital and 2s orbital, and next 2 electrons entering into, means next 2 means fifth electron, fifth electron entering into px orbital and sixth electron entering into py orbital. Okay, but this sixth electron not pairing with the 2px orbital. Okay, about that this will explain. Means electron pairing in orbital starts only when all available empty orbitals of the same energy are singly occupied. Means 2px, 2py, 2pz that are first occupied with a single electron. After that pairing will be start. Means in each orbitals we can keep 2 electrons now. So first two degenerated orbitals are occupied with single electron, then after pairing will be start. For example, oxygen. Now we'll take oxygen. Oxygen atomic number 8. Electronic configuration 1s2, 2s2, 2p4. In that first two electrons will occupy 1s orbital. Next third and fourth electron occupy 2s orbital. And next to 4 electrons will be there now in 2p4. So in that 2p orbital, px, py, pz, like this 3 orbitals are there. Okay, fifth electron entering into px orbital, sixth electron entering into py orbital, seventh electron entering into pz orbital. Okay, so next what about the fourth electron in this 2p4? Okay, in this 2p4 4 electrons are there now. In that one electron entering into px orbital, next second electron entering into py orbital, third electron entering into pz orbital, fourth electron now that is entering into px with opposite spin. Like that it will pair. Okay, oxygen after oxygen after fluorine is there. Fluorine atomic number 1s2, 2s2, 2p5. In 1s2 2 electrons will be there, 2s2 2 electrons will be there. Next 2p5 means 1 electron entering into px, second electron entering into py, third electron entering into pz, fourth electron entering into fourth electron starting pairing with px, fifth electron start pairing with py. Okay, like that will be filled. Okay, means all the degenerated orbitals will be there now that are first singly occupied. Means that all the same energy level orbitals are first that is filled with 1 electron. After the filling with 1 electron, then pairing will be start. Okay, for example, okay, here we discussed in the case of this carbon and oxygen. I think you will understand. Okay, so here oxygen is there, atomic number 8, configuration 1s2, 2s2, 2p4. 1s2 means 2 electrons will come. Okay, with opposite spin. 2s2 means 2 electrons will come with opposite spin. 2p4 means in the 2p4 means we should keep 1 electron in px, second electron in py, third electron in pz, fourth electron we should okay. So here all the three orbitals are occupied with single electron. Now fourth electron pairing with the first electron. If fluorine atomic number 9, in this 2p5 one more electron will be there, that is starting pairing with the py orbitals. Okay, next fluorine neon atomic number 10. So in this 10 electrons will be there, 2p6 will come, that sixth electron starting pairing with the pz orbitals. Like that it will be occupied. Okay, so here one table is given. Complete the electronic configuration of the following elements. Okay, so complete the electronic configuration of the following elements. We should follow the rules. What are that? Can we fill the electrons in the orbital? We can fill the electrons in the orbital according to above principle, Hund's principle. Okay. Here what is that first element name? Carbon. Its atomic number 6. What is its configuration? We can write the configuration by depending on the NLX method, no? Yes or no? Yes, by depending on the NLX method we can write. So carbon atomic number 6. Now how can we write its electronic configuration? 1s2, 2s2, 2p2. Why? Because by depending on the NLX method we can write the configuration. Element is carbon, atomic number 6, its electronic configuration. Okay, 1s2, 2s2, 2p2. By depending on the NLX method we can write now. So first here take carbon atomic number 6. So here we are arranged the electrons in the orbitals. First shell 2 electrons will come, n is equals to 1, that is 1s orbital. Next shell 4 electrons will come, that is n is equals to 2 shell. In the 2s 2p subshells are there. So NLX method means first we will write the information related to n is equals to 1 shell. In that n value is 1. Okay, which subshell? S subshell. And how many electrons are there? 2 electrons are there in n is equals to 1 shell. Now we will write the information related to second shell. So second shell n value 2. Okay, in this how many electrons are there? Total 4 electrons are there. First 2 electrons in 2s orbital, 2 electrons in 2p orbital. Okay, so this is second main shell. Okay, and what is that subshell? Subshell name is S. In that how many electrons are there? 2s2. 1s after electron entering into 2s2 only, no? That's why 2s. How many are there in that 2s orbital? How many electrons we can fill? 2 electrons we can fill. That's why 2 is 2. Next, what is that shell? Next, how many electrons are there? Again 2 electrons are there. In n is equals to 2, total 4 electrons now. Out of 4, 2 will come in 2s shell. Remaining 2 will come 2p2 shell. Okay, so 2s after which shell will come? 2p shell will come. 2s after entering into 2p shell. So here n value is 2 and that subshell is p. How many electrons are there in that? 2. This is the electronic configuration of carbon. Nitrogen, same. Draw the arrangement of electrons in the orbital and write the electronic configuration according to NLX method. If you know this arrangement already, you can write directly also. Okay, so nitrogen electronic configuration 1s2, 2s2, 2p3. So nitrogen atomic number 7, no? So here C once nitrogen nucleus, n is equals to 1 shell. Next n is equals to 2 shell. N is equal to 1 shell means 2 electrons will be there. So n is equals to 2 means 2 plus 3, total 5. 1, 2, 3, 4, 5. Okay, 5. First shell 2 electrons, next shell 5 electrons. 5 plus 2, total 7 electrons. 7 electrons will be there or not there. So n is equals to 1 means in that only one subshell, that is 1s. N is equal to 2 means 2 subshells, that are 2s and 2p. Okay, so now we will write the electronic configuration by depending on the NLX method. Okay, so first we will write the information related to n is equals to 1 shell. So here this n value is 1 and L means subshell. That subshell is which one? S. X means number of electrons. How many electrons are there? 2 electrons are there. 2. Completed. Now we will write the information related to n is equals to 2 shell. In n is equals to 2 shell, how many electrons are there? Total 5 electrons are there. In that first 2 electrons belongs to 2s, means 1s after electron entering into 2s orbital only, no? Means according to above principle, electrons are entering into the orbital in the increasing order of the n plus l values. Okay, so 1s after that electron entering into 2s. In the 2s, yes, 2 orbitals only we can fill, no? That's why we can write okay, so now we are writing the information related to n is equals to 2 shell, no? N value is 2. First entering into 2s, no? So L value what? Yes. Okay, what is that? L means subshell. Subshell, what is that subshell name? S. And that how many electrons we can fill in s orbital? Only 2 electrons. That's why 2 we are written. Okay, na? Next 1, 2, 3, 4. Okay, so out of 5, 2 are completed. Remaining how many are balanced? Remaining 3 electrons are balanced. Okay, so n is equals to 2 shell, no? So now we will write the information related to remaining 3 electrons. Okay, so it is belongs to n is equals to 2 shell. So n value is 2. L means subshell. What is that subshell? 2s after electron entering into 2p only, no? P subshell. In the P subshell, how many electrons are there? 3. 1, 2, 3. 3 electrons are there. This 1s2, 2s2, 2p3 is the electronic configuration of nitrogen. What about oxygen? 1s2, 2s2, 2p4. Same like this also we can write. Fluorine 1s2, 2s2, 2p5. Okay. Neon atomic number 10. Electronic configuration 1s2, 2s2, 2p6. Sodium, atomic number 11. Electronic configuration 1s2, 2s2, 2p6, 3s1. Magnesium 12, atomic number 1s2, 2s2, 2p6, 3s2. Aluminium, atomic number 13. Electronic configuration 1s2, 2s2, 2p6, 3s2, 3p1. Okay. Next, silicon. Silicon, atomic number 14. Electronic configuration 1s2, 2s2, 2p6, 3s2, 3p2. Okay. Phosphorus, atomic number 15. Electronic configuration 1s2, 2s2, 2p6, 3s2, 3p3. Sulfur, atomic number 16. Electronic configuration 1s2, 2s2, 2p6, 3s2, 3p4. Fluorine, atomic number 17. Electronic configuration 1s2, 2s2, 2p6, 3s2, 3p5. Argon, atomic number 1s2, 18. Electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6. Okay. Potassium, atomic number 1s2, 2s2. Potassium, atomic number 19. No. Electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6. 3p after electron entering into which orbital? 3p after electron entering into 4s orbital, not entering into 3d. Why? Because electrons entering into the orbital in the increasing order of their n plus l values. Okay, what is the potassium atomic number? 19. Electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Okay. Calcium atomic number 20. Electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. It is the configuration of calcium. Means here from carbon to calcium we are written electronic configuration. So carbon electronic configuration 1s2, 2s2, 2p2. Nitrogen electronic configuration 1s2, 2s2, 2p3. Oxygen electronic configuration 1s2, 2s2, 2p4. Fluorine configuration 1s2, 2s2, 2p5. Neon configuration 1s2, 2s2, 2p6. Sodium configuration 1s2, 2s2, 2p6, 3s1. Magnesium configuration 1s2, 2s2, 2p6, 3s2. Aluminum configuration 1s2, 2s2, 2p6, 3s2, 3p1. And silicon atomic number 14. Its electronic configuration 1s2, 2s2, 2p6, 3s2, 3p2. Phosphorus atomic number 15. Electronic configuration 1s2, 2s2, 2p6, 3s2, 3p3. Sulfur atomic number 16. Electronic configuration 1s2, 2s2, 2p6, 3s2, 3p4. Fluorine atomic number 17. Its electronic configuration 1s2, 2s2, 2p6, 3s2, 3p5. Argon atomic number 18. Electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6. Potassium atomic number 19. Electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Calcium atomic number 20. Electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So these are the electronic configuration of the elements. Okay. So you can write the electronic configuration of the other elements also. So you can write the electronic configuration of the other elements also. Once you write the electronic configuration of 21 to 30 elements. Okay. To write the electronic configuration of the elements, you can take the help of the Euler chart also. Okay. Once you try to write. Okay. So what we learned in this class? We learned in this class about chromatic spectrum and Bohr model, Sommerfeld model, quantum numbers. Next, we discussed about principal quantum number, azimuthal quantum number, magnetic quantum number, spin quantum number, and we discussed about the electronic configuration and above principle, Hund's principle, and Pauli exclusive principle, and how to write the electronic configuration of a atoms we discussed. Okay, so like these elements are there now, nearly 118 elements are there, how these elements will be arranged. So it is difficult to remember the each and every element name and its properties. So our scientists, they try to classify the element. About the classification of elements we will discuss in the next chapter.